In section 8.2, there are several right-hand rules explained. And so I just want to run through those quickly just so you can kind of see those. There's 3 right-hand rules. Right-hand rule number 1, so this one up here, there was 2 different pictures on the slide, but what it's showing is if there's a wire carrying current, so right up through here, if there's a wire carrying some current, that current, that electrical current, actually produces a magnetic field. Okay, so if my pencil was a wire carrying current going in that direction, let's call it north, then what I would do is I would point, it's got to be my right hand, I would point my thumb in the direction of that conventional current, and my fingers would wrap around as I kind of grab onto the wire. My fingers would wrap around in the direction of the magnetic field. So the magnetic field is kind of going underneath to the left, and then it's coming up over here, and it's going to the right over the top of the wire. So it's kind of spiraling around the wire. Just a couple quick notes. This is for conventional current. Conventional current is the flow of positive charge. If you know any electricity, positive charge actually does not flow. So a long time ago when people started coming up with this stuff, they assumed that positive charge is what flowed. Turns out it's actually negative charge that flows, but all of these right-hand rules still work. We just have to remember if electrons are actually flowing this way. Okay, so let's put a little E here. If electrons are flowing in this direction, that means conventional current, I, is flowing in the opposite direction. Okay, so that's a little confusing, but all these right-hand rules are going to assume conventional current, flow of positive charge. If the positive charge was flowing this way, what that really means is negative charge is flowing the other way. But if positive charge flows this way, we grab with our right hand, and the fingers kind of show the direction of the magnetic field, the B field. Okay, that's the magnetic field. Right-hand rule number 2 is for solenoids. Solenoid is basically like a slinky. I couldn't find my slinky. All I could find kicking around my house here was a spring. But if you took some wire and wrapped it around something, so let's say I had my pen and I wrap some wire around it, what I've got is what's called a solenoid. If I pass electrical current, so again, electricity, if I pass electrical current through here, it's going to create a magnetic field. And this time the magnetic field is going to be down like through the center of the solenoid, so kind of going inside of the solenoid. So if my conventional current, again, it's conventional current, so just kind of keep that in mind. Electrons are actually flowing in the opposite direction, but if conventional current is spiraling around the solenoid, like inside the metal, if it's kind of going around this way, I'm going to point my fingers of my right hand in the direction that electric conventional current, the flow of positive charge, is going. My thumb then is going to point in the direction of the B field through the center of the solenoid. Okay, so if you can look at my picture here, there's going to be a B field kind of going in this direction. B field is magnetic field. It's going to be going in this way. There's B field kind of coming in that way, and it's kind of coming out this way. It's going to kind of wrap around like this, but let's say it's going out this way, and it is going to wrap around, and here it's going to kind of come around on the outside. But what we usually talk about is not the B field going this way. The B field out here outside of the solenoid is really weak. Down through the center of the solenoid, it's very strong. Okay, so our thumb points in the direction of the magnetic field, the B field, through the center of the solenoid. If you could picture this like a bar magnet, then the north side of the magnet would be here, the south side of the magnet is here. Magnetic field, B field, points out of the north end into the south end. And again, it's going to wrap around like this, so it's kind of going back this way. Same thing over here, kind of coming around this way. But this solenoid, so again, a solenoid is just like a slinky or a spring or something, but with current running through it. That solenoid behaves like a bar magnet. So it has a north end and a south end. The last one is everybody's favorite, usually, hopefully. When I look at right-hand rule number 3, it's maybe the most complicated. You'll see it done different ways. Sometimes people use 3 fingers like that. So thumb is pointing in one direction, fingers pointing in one direction, third finger is pointing, or middle finger, I guess, is pointing in one direction. To avoid the obvious, middle finger coming up at some point, some people will use 3 fingers there. That looks a little bit nicer. Most textbooks now or websites now will go to just palm, because that way we can avoid the middle finger. So what's happening for this one is my thumb is pointing in the direction of current. Again, that's conventional current, so flow of positive charge. Thumb points in the direction of conventional current. Your fingers point in the direction of the magnetic field, and your palm, so kind of pointing out this way from my palm, say perpendicular to the other two, is the force. What this is for is if there's like a wire, so if I had, oh, that's not a very good wire, if I had a wire carrying conventional current flowing in this direction, and there was a magnetic field, here it's kind of, going this way, but I'll draw it just kind of going this way. If there was a magnetic field here, wherever this wire carrying conventional current sits in a magnetic field, it's going to experience a force. So if current is kind of going up that way, let's call it north, B field is going this way, let's call that west, then my palm points straight up towards the camera in this case, maybe coming out towards you as you're watching this video. The force is going to be coming straight out, and the symbol that we use for that is here. This was, I think, slide 3, where this symbol means kind of coming straight out towards you. Just as a side note, if the force was going in the opposite direction, it's not here, but if it was, we use this symbol. This is supposed to kind of look like an arrow, so this is like, if you can see an arrow coming straight out towards the camera, wherever my camera is, it kind of looks like just a point with a circle, whereas this side is supposed to look like the tail feathers. If I had tail feathers on an arrow, that's what we're seeing there. So this one we call out of the page, into the page. Yeah, that's our right-hand rule. So we're going to try a couple of these, the maybe a little bit trickier ones. And this is on slide 7. So let's focus one at a time. We'll call this 1. And as we run through these, I'm going to kind of pause a little bit, and I want you to try to think about what the direction is. Okay, so what we've got is a positive charge going this way. It's sitting in a magnetic field. So imagine this magnetic field is all throughout this area. It's all coming like out towards you, a whole bunch of magnetic field coming out towards you. Okay, so think about it for 1 sec. If you want, pause the video, see if you can work out what direction the force is going to be. I'm going to start walking through it, and again, if you think you can figure it out, pause it as some practice. So conventional current, positive charge is going that way. This is right-hand rule number 3, by the way. The B field, so I'm going to take my fingers out, the B field is coming straight out towards you this way. The force then is kind of, I'm blocking in shadow here, but the force is going that direction. Okay, so the force is going to be going this way. This charged particle, as it enters this magnetic field, it's going to experience a force that way. If I was to say this on my page here with a little north, east, south, I would say the force is south. Okay, so on my page, it may not look like that when you're watching the video, but moving over to number 2 then. So again, if you could do this one, maybe pause the video, see if you can work this one out. I'll keep going. An electron now is moving this way. Okay, again, this is right-hand rule number 3. If an electron is going this way, that's actual electricity kind of flowing. Conventional current is going to flow in the opposite direction, okay? So my thumb is going to point to my left, or west, I guess you could say. My fingers is the B field. It's going to point that way. In this case, the force is straight down. It's kind of like if I was to push my page straight down. So the force that this guy experiences is into the page, and we just talked about that symbol. There's the tail feathers of an arrow as it goes into the page. Okay, so just running through that one more time. If a negative charge is moving this way, that's the same as conventional current flowing that way. Okay, so my thumb points that way, my fingers point north, force then is straight down. And again, we try to avoid the words up and down. We'll say into the page or out of the page, just to avoid confusion as to what direction is up and what direction is down. Last one then, number 3, again, pause the video if you think you can work this out. Just something to note, I and B do not need to be at right angles. So if I'm using my right hand like this, here's I, here's B. I haven't lined it up yet to this, but here's I and here's B. They do not need to be at right angles, okay? So I can be at some other angle to B. So in this case, I is kind of going that way, B is kind of going this way. The force, according to my palm, is pushing straight out towards the camera. Force then is this way. All these are vectors, but force is kind of out towards the camera. That's the direction of the force. Just something to notice here, the equation F equals QVB sine theta. That's the equation that we're using. So the equation itself is pretty easy. Just a couple things to note with that equation. Everything here is magnitude only. Okay, so we're not going to sub in any signs. We've kind of seen stuff like this before, but if I'm looking at number 2 here, I'm not subbing in a negative here. V, it is a vector, but I'm not, it's just magnitude, it's just speed. Same with the B field. I'm just subbing in all the numbers for Q, V, and B. Theta is the angle between them. Okay, so here you could say theta is 150 degrees. I'm actually going to use 30 degrees, okay, the angle between I and B, or between V and B. And again, when we talk about V, we're always talking about the positive charge. So if V is this way, we're actually going to turn it around and point it in the other direction. Because of some symmetry with sine, it's actually not going to matter which angle we use, but we typically, as a standard, just use the smaller angle. We sub in all of our numbers, we're going to get a force, but in order to know the direction, we're going to use this right-hand rule number 3 to figure that out.